All right, hello everybody. So I'd like to welcome you back to the remainder of Chapter 6. And today we're going to be looking at the central limit theorem, which in your section of the Triola book should be section 6.4. All right. Now, what we ended with last time was that last time we were looking at these sampling distributions. And we ended where we started looking at these unbiased estimators. And we kind of want to continue with that whole process. All right. So within that whole process, finding these unbiased estimators or identifying these unbiased estimators is going to be what we want to do. So in here, where we start is we're going to be looking at these conclusions that the distribution of a sample the distribution of sample means, x bar, will approach A, and this will be normal distribution, as the sample size increases. All right? So when we start looking at the sample sizes that we're doing or that we're taking, the more of these samples that we take, the more that the mean of those samples will start approaching a normal distribution. All right, so that means that this distribution that we look at may or may not be normal. In other words, it may or may not be symmetric. Now, that's going to play out on a grander role. All right, now number 2, it says that the mean of all sample means is the population mean, and that's going to be just mu. Now, this result here is kind of what we ended with last time, in the sense that I said, hey, look at these two items here. Remember these notes over here, where I said, hey, look at this mean, and then look at this mean of the means. Both of them are the same, which means the sample mean is going to just be the same as the population mean. And we said that the mean was an unbiased estimator. Now, for number 3, the standard deviation, like I said above, is not an unbiased estimator. However, we can still calculate the sample standard deviation for these for the sampling distribution if we take the population standard deviation and if we divide by the square root of n. Doing this will give us exactly what we're looking for, which is the standard deviation for the sampling distribution. All right. Now, we need these two items here. These two items are going to be super important for us moving forward. All right. So I'm highlighting them in red because, again, they're super important topics that we need moving forward. Now, here are these two notes. These two notes. Number one, if the original distribution is normally distributed, then for any sample size n, the sample means will be normally distributed. All right, awesome. So if our original distribution is normal, then any sample means that we take or any samples that we take will automatically be normally distributed as well. Number 2, if the original population is not normally distributed, and there's a key, it might not be normally distributed, it might not be normally distributed, but for sample sizes greater than 30, wow, I forgot to change that back, there we go. For sample sizes greater than 30, the distribution of sample means can be approximated by a normal distribution. So what I want to do here on this example, this says that I want to find the mean of the sample means, and I want to find the standard deviation of the sample means. They're only giving us the population mean and the population standard deviation along with the sample size that we're looking at. Notice the sample size does not satisfy number 2 here. However, it only needs to satisfy one of them. So I'm going to put these in red. That says only one condition needs to be met. So either condition 1 or condition 2. If it meets both of them, great, right? But typically it can't because, again, normally distributed, it either is or it isn't. So here we go. Let's find the mean of the sample means. Well, since they're telling us that this initial population is normally distributed, that means that under these assumptions, the mean is just going to be 10, because that's a population mean. The standard deviation of the sample means is going to be 3 divided by square root of 9, which simplifies to be 1. Now, under this assumption, whenever I start looking at my population and I start then taking these, I then start taking these samples are going to be a little bit more, let's say, compact. The normal distribution is still going to look normally distributed. However, it's going to have a steeper ascension and descension. All right, meaning that this particular standard deviation is going to look more like if it's all squished together. All right, sorry, I said normal distribution. This normal distribution is going to have a smaller standard deviation here. The next one, given a distribution with 77 as a population mean, standard deviation of 14, sample size of 49. Notice they don't give us that the population is normally distributed. We don't need that if the sample size is greater than 30. So again, one of these conditions must be met, and it seems that this one's going to meet condition number 2, so that's perfectly fine, which means we can still find the mean of the sample means, which is going to be 77, and the standard deviation of the sample means, in this case it's going to be 14 divided by square root of 49, that's going to be 7, so that's going to be 2. Now, what happens here, as we start looking at our distribution, it doesn't look normal. But because we're going to take samples, this sampling distribution will be approximately normal, which again means that we're going to be looking for a normal distribution when we take these sample means. All right, so here we go. Steps that we're going to need to take. Number 1, check if X bar is normal. If it's not, then is the sample greater than 30. Number 2, we're going to use that information to then get us the mean of the sample means or the standard deviation of the sample means. Number 3, we're going to use normal CDF for the rest of the information. In other words, we're going to use normal CDF that once we have this normal distribution, we're going to want to calculate a probability. So here goes your first example. On this first example, it says that the GPA of all students enrolled at a large university have a normal distribution with a mean of 3.02 and a standard deviation of 0.29. Key phrase here. It says that we have a normal distribution. Not only do we have a normal distribution, but they're actually giving us the mean of that population, which is 3.02, and they're giving us a standard deviation of 0.29. So I'm going to extract that here. Mean is 3.02. Standard deviation is 0.29. There we are. Great. Now, what I'm going to want to do here on this example, it's asking me, part A, it's saying, hey, find the probability, so I need to find a probability that one randomly selected student will have a GPA that's greater than 3.20. All right, so let's go through that probability notation. So probability that a randomly selected student, I'm going to label as X, has a GPA that's greater than 3.20. Okay, so now I need to use a z-score, right? Because if we want to use probabilities here, typically we want to normalize everything and work with that normal distribution like we did in the previous section and the section before that. All right, so back in 6.2. So let's normalize all of this. 0, 1, 2, 3. And I'm going to write down that these are z-scores. -1, -2, -3. There we are. All right, so let's go ahead and normalize. Probability that some z-score is going to be greater than something. All right, well, let's find that something. We're going to take the x value. What's the x value? Well, that's 3.20 minus the mean, which is 3.02, divided by the standard deviation. The standard deviation is that 0.29. There we are, just like that. Which now means that we're supposed to be able to calculate this z-score. All right, so let's go through and let's calculate that z-score there. All right, so that's 3.20 minus 3.02. That's going to get us 0.18. So 0.18 divided by 0.29 should get us 0.62. And remember, this is a z-score, so I just want to keep using that z-score with 2 decimal places. There we are. Now what I'm going to do is I'm going to go to normal CDF, and I'm going to calculate that probability. All right, so 0.62, I'm going to shade all of that in really quickly. So let's find that 0.62, so that's going to be somewhere here. 0.62, and I'm going to shade everything to the right, because again, I want the z-scores to be greater than those values. There we are. And so again, I'm using a right tail test, or sorry, a right tail test, excuse me. This area extends to the right, which means it goes to the right tail. So I'm going to go through and we're going to go do this on the TI-84. So follow me along. All right, here we are with the TI-84. Let's go through the distribution. Normal CDF. I want the lower bound for that bounded region, which was 0.62. The upper bound was that 1E, oops, excuse me there, 1E99. Mean and standard deviation were both 0. Paste it. Here we are. Which means we should get a probability of 0.2676. So let's go through and let's write that down. All right, here we are. Now for test purposes, I'm going to say I was using normal CDF. And here I input 0.62, 1E99, 01. And just to reiterate, when you do an exam in my class, you have to show me what command you're using on the calculator. Since we're not doing this with tables, you have to go through and show me those calculations. All right, there we are. So there's exactly what we need. That's it. Nothing else. We're done. Great. Part B. For part B, it says that we need to find the probability that 25 randomly selected students will have a mean GPA greater than 3.2. Okay. So here is where we need to use that central limit theorem that we were talking about at the very beginning of this section. So what I'm going to do here is I'm going to use the central limit theorem. So use the central limit theorem. The central limit theorem just basically says, can we use normal CDF? Well, we have to go through and we have to check if we can use normal CDF. The way we check is 2 ways, right? Conditions must be satisfied, one or the other. Number 1, is the population normally distributed? Or number 2, is the sample greater than 30? Well, here, the sample is not greater than 30. However, the population is normally distributed. So this checks out because, again, we have a normal distribution for the population. So population is normally distributed. Nice. All right, so that checks out. All right, so let's go through and let's start extracting now. If we're going to be using normal CDF, then we need a mean and we need a standard deviation to work with. All right, so we can start extracting that mean and that standard deviation that we need to work with. All right, so let's go through and extract that. The mean, what's the mean of all of the samples? Because again, we're looking at 25 of them. Well, according to our work before, it's just the mean of the population, which is 3.02. What is the standard deviation that we're going to be using? If this is, again, a random sample of 25 students, we need a sampling distribution, which means we need to calculate it using this. So that's 0.29 divided by the square root of n, and that's going to be the square root of 25. All right, let's go through and let me just double check real quick. 0.29 divided by 5. All right, we should get 0.058, so we get exactly 0.058. Nice. So if we want to find now the probability that 25 randomly selected students will have a mean GPA. So now be careful here. Out of these 25 randomly selected students, they need to have a mean GPA greater than 3.20. Notation-wise, that's going to tell us that the sample that we choose will have a mean greater than 3.20. And again, look at the notation difference between Part A and Part B. Part A is a randomly selected individual. Part B is a mean that's greater than 3.20. So now let's normalize all this. The probability that some z-score, that some z-score is going to be greater than, well, let's see what's in question. What's in question here is that we got 3.2. That was at 3.20 minus my mean of 3.02 divided by, and this is where we have to be very careful, the standard deviation of the samples. So the standard deviation of the sample means was at 0.058. All right, this is going to give us our z-score. So looking at the z-score, I'm just going to go put this into the calculator. So 3.20 minus 3.02, and then we're going to divide that by 0.058, and that should get us approximately 3.10. So standard deviation wise over here, or sorry, normal distribution wise here, 0, 1, 2, 3, negative 1, negative 2, negative 3. What we're looking for here is we're looking for the mean to be greater than the z-scores, where the z-scores are 3.10. So that means it's somewhere over here. Really, really tiny probability. All right, I'll shade it in right there. So let's go through the TI and let's plug all this in. All right, here we go. All right, here's a TI. We're going to go to normal distribution. There we are. Lower end, what was that lower number? That was for the area that's bounded, that was 3.10. Largest upper bound, again, we don't know what it is, so we're just going to go with 1E99. Mean and standard deviation, we're both going to be 0 in this particular case, because again, we're working with z values. Hit enter, and we get this probability. It's a really, really tiny, tiny probability, because again, here, right in here, we're looking at scientific notation. So scientific notation wise, we now have to interpret that. So let's go back to the board and let's go ahead and reinterpret that there. All right, here we go. So my calculator gave me this. It said, or actually I'm going to do the work on the side on the scratch piece here. and then I'll redistribute it over there. So calculator, let me do this in, yeah. So my calculator gave me 9.676712349 E, and then it said -4. This is really just 9.67671239 times 10 to the power of -4. What does that -4 do when it's being when it's the exponent on that 10? Well, it's going to bring this decimal to the left, and it's going to move it 4 times, just like this. 67671239. And so again, this decimal was moved 4 times to the left. So it was initially here, and then it went 1, 2, 3, 4 to wind up there. Nice. There we are. All right, so this is the number that I want. That's the probability. So as I'm looking at this probability, what I'm going to do is I'm just going to round it. 0.000, and then I'm going to say, hey, right here, this is just going to round to 1. So probability here on the paper now. This is 0.0001 as my probability. In other words, it is a very, very tiny, tiny probability, almost insignificant. All right, so this is going to be 1, 2. That's about 0.01% chance of this happening. All right, nice. So that's how we're working with this, and that's what we want to see. Now let's look at the next example. For the next example, we want to find the probability that 10 randomly selected students will have a mean GPA between 2.9 and 310. All right, so again, I want to find a probability here, and that probability is going to be for 10 randomly selected students, and they're giving me, or they're telling me that I need to have that probability be greater than the mean GPA, or bounded between these two values. And that's going to be between, 2.9 and 3.1. How does that look like? Well, that's going to look like this. Probability that the mean GPA is between 2.9 and 3.10. There we are. Nice. So, the process here, can we normalize this? Yes, we can. We're going to use the mean, and we're going to use the standard deviation. All right. Now, when we use the mean and when we use the standard deviation, we have to be really careful here. All right. Now, specifically because if I want to find the mean of the samples, well, that's just the mean of the population. But the standard deviation here is the standard deviation of the population divided by the square root of n. Notice in this problem, n is different than the previous problem, which was part B. And in this case, this is 0.29 divided by the square root of 10. So again, be very careful. Now, do I want to normalize this? Some of you may answer yes, some of you may answer no. In section 6.2, I walked through a few problems where I said you don't really need to normalize these problems. You can do it without normalizing. In other words, you can do it without going into a normal CDF and identifying that we have 0 and 1 as a mean and standard deviation, respectively. So what I'm going to do instead is I'm just going to jump straight into normal CDF. Now, why am I going to jump straight into normal CDF? Well, there's going to be a few items that I'm working with here that I'm going to share with you all. All right, normal CDF. Lower bound of the shaded area is 2.9. Upper bound is a 3.10. Mean it's that population mean, which is 3.02. Standard deviation, I'm going to use this exact standard deviation. I'm going to use 0.29 divided by the square root of 10. And I'm going to insert this into the calculator exactly as it is. So follow me to the TI and we'll go ahead and we'll get that done. All right, here we are back at the TI. Let's go through, access that normal distribution. Normal CDF, there we are. Lower bound. That lower bound that we wrote in, that was at 2.9. Because again, we didn't normalize this. We didn't standardize it, so it's fine. The upper bound, that was at 3.1. The mean was the actual mean that we're using, which was at 3.02. And the standard deviation, I am not going to approximate that standard deviation. All right, so looking at that standard deviation, that was our 0.29, I believe. So I'm going to type in 0.29, and then it was going to be divided by the square root of 10. The square root, it's right here. I'm hovering my mouse over it. So I'm going to hit second square root. There we are. And then I'm just going to type in 10. Close that parenthesis. There we are. Press enter. And let's go paste that formula. There we are. So notice that normal CDF right now looks exactly as I had written it on my sheet of paper. Normal CDF, lower bound, upper bound, mean, and standard deviation. And we're going to press enter just so that we can get our value. The probability here is 0.713. So let's go ahead and let's write that down. Here we are, which means the probability is approximately 0.7131. There you are. That's it. So, as we then start looking at this, we always have to ask ourselves, what are we trying to find? Is it a probability or is it a z-score? If it's a probability, is it just a randomly selected individual like it was in part A, or a randomly selected object? All right. Number two, if it's not a randomly selected object or person, is it a randomly selected sample within the population? And that fits the scenario for part B and C. So when you're doing this, again, there's a few items that you need to ask and that you need to look for. Once we start looking at them and once we start finding them, then we can go ahead and fill everything in. So let's look at this next example. This next example says that we're going to let X equal to the CEO salaries in thousands. And this is going to be where X is skewed right, and they give us the mean and they give us a standard deviation. That's awesome. Now, part A. If all possible random samples of 40 CEO salaries in thousands are taken, how would you describe the distribution of sample means? So the question is here, how would I describe the distribution of sample means? Well, I have to then look at something. And this is what I'm looking at. The population is skewed right. But wait a second. How many samples are we looking at? 40. Which means what gets applied here, we need to apply the central limit theorem. Applying this central limit theorem is now going to help us to identify how we are going to describe the distribution of sample means. Well, according to the central limit theorem, the distribution of sample means is normally distributed because n is greater than or equal to 30. And that's because we're given 40 of those samples. Awesome. So what would the standard deviation of the sample distribution be? Well, the sample distribution here, the standard deviation for the sampling distribution, would just be the standard deviation divided by the square root of n. Well, in this case, it would be 139 divided by square root of 45. All right. So, can we get an approximation for this if we'd like? Sure. Take 139 divided by the square root of 45. I get this natural standard deviation to be 20.72. All right. Great. Oh, excuse me. Wow. Yeah, somebody caught that mistake. Thank you. It's not 139. My apologies. It is 45. 45 divided by square root of 40. My apologies there. Wow. 45 divided by square root of 40. This shelter in place is really getting to me. Whew. All right, so this is approximately 7.12. There we are. Very nice. Now, what this means is that if our population is skewed right, that doesn't matter to us, because as we start looking at the sampling distributions are going to give us a normal distribution for them. So, that's part A. Let's look at part B. What is the probability that the mean salary of a sample of 40 CEOs is between $137,000 and $145,000? So let's dissect this a little bit. We want to find a probability. We want to find a probability that the mean salary of a sample of 40 employees, so they're telling us, hey, we're taking a sample of 40, so it's not one individual, is between 137 and 145. Let's write that out. Probability, and this is going to be between 137, and remember, I want the mean, in other words, the sample of that mean to be between these two given values. Now, I heard somebody in the back, yes, you're right. It doesn't have to be equal to, but remember, since this is all continuous probability, it could be equal to underneath those inequalities, and it still wouldn't make a difference because we would get the exact same answer. So, let's go through. Since this is an interval, I don't want to normalize two z-scores, so I'm just going to go ahead and use my normal CDF. Lower bound is 137. Upper bound is 145. Mean, what was the mean given to us? Well, I believe the mean of the CEOs, that was at 139. Standard deviation was the one that we calculated, which was the one where I made those mistakes, which was 45 divided by square root of 40. We're going to go through and we're going to put this into the TI. So, follow me along with your TI. Here we go. Let's go with the normal CDF. Perfect. Lower. What was that lower bound for the area? That was that score of 137. Upper bound? That was 145. Mean? 139. Standard deviation? That was 45 divided by square root of 40. Oops, excuse me. Square root of 40. There we go. Press enter. Enter. There we are. So here's the formula exactly as I had it written down on the sheet of paper. Let's press enter. Boom. 0.411. Let's go back and write that down. Here we are. Approximately 0.4111. Nice. Now let's see if we can go ahead and we can fill this table in. Now the mean was 139. Standard deviation. That standard deviation that we're using here, well, we have to go back and interpret which one we're going to be using. we're using this standard deviation here, which is at 45 divided by square root of 40, which again we said was about 7, somewhere around there. So the standard deviation that I'm going to use is about 7, which means I add 7 here and I get 146. I subtract 7 from here and I should get 132. Look at that interval. That interval goes from 137, somewhere here, to 145, which is right here. And there's a probability, or there's the area that we're looking for. That probability is, or that area there is 0.4111. That's what we found. All right, perfect. So let's work on the next problem, part C. All right, so for part C, we're asked that given a sample of 40 CEO salaries, at what mean salary does the top 10% of the CEOs begin at? So the question is now, at what mean salary does the top 10% begin at? So are we looking for a probability? No. Perfect, we're not looking for a probability. They're actually giving us that probability value. They're saying the top 10%. So in other words, they're giving you this percentile, which is the top 10 percentile. So what we look at here is just the top 10%. So let's try to find that top 10%. I don't know, I'm just going to shade in a random area here, and we'll see if it's right. If it's not, then we'll go ahead and we'll adjust it. So here we go. That area here is at 0.10, because again, it's the top 10%. All right. Now I want to find an inverse, right? Because I want to find a z-score. So use inverse norm to find a z-score. And I'm putting quotations here that we're not exactly finding a z-score, because in this particular question it's saying what is the mean salary. In other words, what's the average salary? It doesn't say what's the average z-score. Now that's going to pertain to this question here, to part B, because I want to look at something for part B. For part B, I still use normal CDF even though I didn't normalize this. Look at the previous question as well. The previous questions. Look at part B here. In part B, I was looking for a mean, but yet I normalized it. Part C, I didn't normalize, but I was still allowed to use normal CDF. That goes back to what I'm trying to look at here, that if I can use inverse norm to find a z-score, could I possibly use inverse norm to find a salary? Sure. Here, we're going to get the salary, which is going to be the inverse norm. And instead of putting in a standard normal score, which would include a mean of 0 and a standard deviation of 1, I'm actually going to go through and input what I know. My area that I have is 0.10, or in other words, 10%. I need a mean. The mean is 139, right? Because that's the same mean that we're using from before. I need a standard deviation. The standard deviation of the samples. What was that standard deviation of the samples? Well, that was that 45 over square root of 40, which means this is 45 over square root of 40. And I want this to the right, like such. Let's go to the TI and let's input this in. All right, here we are. Let's access that normal that inverse norm. So I'm going to go to second, same thing, distribution. I'm going to go to number 3, which is inverse norm. There we go. The area, that was that 0.10. Perfect. The mean, again, I'm not standardizing this, which means the mean is just 139. Standard deviation, I'm not standardizing it, which means that's 45 divided by the square root of 40. Close that. I want it to the right. There it is. Hit enter. Oh, excuse me, hit down, then enter. There it is. Inverse norm, 0.10, 139, 45 over square root of 40, and to the right. Boom. We get an answer. We get an answer of 148,000.1183. Let's go ahead and let's write this down. All right, so let's go back to the page. Here we are. So the salary that we get here was approximately 148 let's round this off to about 148.1. And I'm going to say the salary for the top 10% of CEOs begins at $148,100. That's it. Awesome. So I want you all to try part D. All right, give part D a shot and see how you do. All right, I'll post up the answer in just a bit, so take some time, put pause on the video, and give it a shot. All right, here we are. Let's start working with it. I highlighted all the sections or all the verbiage that we need. We want to find the probability that the mean salary of the sample of 40 CEOs is less than $120,000. So let's go through and let's figure this out. I personally want to normalize this because these are going to be large numbers, but again, you don't need to normalize it. It's okay. We'll still get very similar answers. Minus the mean, which is 139, divided by the standard deviation, which was 45 over the square root of 40. There we go. So this probability is going to be that the z-score is less than negative 2.67. Going to my normal normal CDF. Should get normal CDF, negative 1E99, comma, negative 2.67, comma, 0, comma, 1, which should get us approximately 0.00379. There we are. Is this unusual? What does unusual mean? Unusual means that it's going to be less than 5%. In other words, 5%, that's just 0.05. So is this number less than 0.05? Yes. So yes, it is unusual. All right. And why is that? Because that's less than 0.05. Awesome. There you have it. So if this was 0, negative 1, negative 2, negative 3, I want negative 2.67, so that's going to be the area to the left, shade area to the left there. And there you have it. That's it. Yay. We're now done with chapter 6. Awesome. So I'll go ahead and upload this video. That way you guys can take a look at it, and I will see you all next time.